in this video we're going to be looking at primes, prime numbers. A positive integer p greater than 1 is prime, or is a prime, or prime number, if its only positive factors are 1 and p. In other words, the only true divisibility results we can say are that 1 divides p and p divides p. Or if you like, if x divides p, then x must either be minus 1 or 1, or minus p or p. A positive integer that is not prime is called composite. So a composite number is a number that has factors that are not plus or minus 1 or plus or minus p. So let's have a look at some simple results on prime numbers. Here are the first 6 prime numbers: 2, 3, 5, 7, 11 and 13. Second simple result we might want is that there are in fact infinitely many primes. This is a fact that's been known for well over 2,000 years, and you'll look at one of the many proofs of this result in chapter 3 of the course, possibly the simplest and oldest result, proof of this result. The largest known prime is, well, it's going to change, and I'm not going to say what it is as I film this video, because it could have changed by the time you view it. I'll leave you to do an internet search for what it is, just put in largest known prime. It will have tens of millions of digits at the least. Fourth little result here says that integer is composite if and only if it can be written as a product of 2 integers greater than 1. Our definition of composite, remember, is that there is at least one other factor. So this is saying just a little bit more. Here's a couple of examples, or 3 examples. 4 is 2 times 2, 6 is 2 times 3, 910 is 91 times 10. They're all composites, all written as a product of 2 integers greater than 1. So let's have a look at the proof. It's an if and only if, so we're going to have to go in 2 directions. Firstly, a number n is composite. If a number is composite, I should say, then it has a factor a, where a must lie somewhere between 1 and n. Now, if a is a factor of n, then that means a divides n, so there must be a b with n equal to a times b. Now, we already know that a is not 1, but we can easily see that b can't be 1, because if b were 1, then a would have to equal n, and we know that a is not n. So here we've got n written as a times b, where neither a nor b is 1. Conversely, if n is a times b, where both a and b are bigger than 1, then neither a nor b can be n. So n has factors that are not 1, one of a and b, or both of them rather, and therefore n must be composite. There's one other very important property of primes that gives them their real utility when you go on to more advanced work, and it's this result here. If p is prime and p divides a product a times p, then it must divide either a or b. It could in fact divide both. The proof of this fact is one of the problems in chapter 3 of the course, in the proof theory section. When we want to check whether or not a number is composite, we would try dividing it by other numbers, and we'd in fact use primes. We'd want a list of primes to do this, and towards the end of the video I'm going to talk a bit about how you would create, one way anyway, of creating a list of primes for which you could do this. How would you test for divisibility? Well, you could use divisibility tests if you had them, but if you didn't, you just have to do long division. I'll come back to this topic later on in some extra material, but what I want to do now is to go on to looking at how do we actually find prime factors. Testing for prime factors by trial division, if that's all we can do, it's a very primitive method, but in fact it turns out to be useless unless we know all the primes up to, well, it's actually up to the square root of n. Not n itself, the square root of n. Why only the square root? Well, it's because of this result. Theorem says that n is composite. If n is composite, then it must have a prime factor less than or equal to the square root of n. Now this is actually a relatively easy result, and you'll find it covered in chapter 3 of the course again. What I'm going to do is prove what's in fact an equivalent result, which is if no prime less than or equal to root n divides n, then n in fact must be a prime number. And we do that by contradiction. So let's suppose that no prime less than or equal to root n divides n, but nevertheless n is a times b. N is composite, with neither a nor b equal to 1. Now, it can't be that a and b are both strictly larger than root n, because if you multiply 2 integers larger than root n together, you get an integer larger than n, but a times b is supposed to be n. So one of a or b must be less than or equal to root n. And we're going to assume, without loss of generality, that it's a. If it happens to be b, then you just rename a and b. It doesn't make any difference. That's what we mean by without loss of generality. So a is less than or equal to root n. Now, A can't be prime because we've assumed that A has no prime factor this small, so it must in fact be composite. And if A is composite, it must have a prime factor, P, and that prime factor, a proper prime factor, must be less than N. Because A is composite, it must have factors. There must be some prime factor there. So A has a prime factor P, which is less than A, but P is less than A, and A is less than root N. And in fact, P must be a prime factor of N itself, because P divides A and A divides N, that's what we've assumed, so it follows that P divides N by transitivity of divisibility, which we proved in the previous video. And that's a contradiction of our hypothesis. I've got a prime factor of N less than root N. So it can't be that N is composite, N in fact must be prime. Let's turn to looking at an example. Let's look at how we prove that 103 is prime. Now I invite you to pause the video for a bit here and go through the proof yourself as a bit of practice. What do we have to do? Well, square root of 103 is strictly less than 11, it's just 10 and a bit. So we would need to check divisibility by the primes that are strictly less than 11. That's 2, 3, 5 and 7. Now we've actually got tests for the first three of these from the previous video. Firstly, we know that 2 is not a factor of 103 because 103 is an odd number. In fact, we only need to know that 3 is an odd number. So we're not divisible by 3. Well, the sum of the digits, 1 plus 0 plus 3, is 4, which is not divisible by 3, so it follows to 103 is not divisible by 3. That's our divisibility test for 3 that we saw in the previous video. Since the last digit is neither 5 nor 0, 5 doesn't divide 103, so the only thing we've got left to check is 7. And, well, there is a divisibility test for 7, but it's not actually any useful in a number like 103. Best to be done by long division. You try and divide 7 into 103 and you find you can't do it. 7 into, well, long division, 7 into 10 goes once, carried 3, 7 to 33. Well, 33 is not a multiple of 7, so 7 doesn't divide 103. And that's a proof that 103 is in fact a prime number. So, we've seen that composite numbers can always be written as product of smaller numbers. But we don't have to stop there. We could take those smaller numbers and find factors of them as well, assuming they're composite. Now, we can't keep doing this forever because there is a smallest composite number. I'll leave you to work out what it is. And of course, if at any stage we get a prime, well, there's no more factors to be done there. So it suggests that we could always take a composite number and write it as a product of prime numbers. Let's have a look at an example. Right? This is what we're going to try and illustrate here, that every positive integer can be written as a product of primes, the product known as its prime factorization. Our example here is going to be 60. Well, 60 is a composite number because it's 6 times 10. Right? 60 is 6 times 10, but both 6 and 10 are composites. 6 is 2 times 3 and 10 is 2 times 5. So there's 60 written as a product of prime numbers. But that's not the only way we could do this. We could have thought of 60 as 4 times 15, and 4 and 15 are both composites. 4 is 2 times 2 and 15 is 3 times 5. So 60 could also be written as 2 times 2 times 3 times 5. So these are two different ways we can factorize 2 as a product of primes. Well, actually not really different, are they? Because multiplication is commutative, and associative in fact as well, so the order and the way you group them doesn't make any difference. So these two prime factorizations are really the same prime factorization, and this gives us our first major theorem of the course, or this section of the course, the fundamental theorem of arithmetic. Every integer n bigger than or equal to 2 can be written uniquely as a product of a finite number of primes, which you can write in increasing order. And here we see n is p1 to the m1 times p2 to the m2 up to pk to the mk, where p1 strictly less than p2 and so on, and all these m's are integers. Now, this, by the way, is why we don't have 1 as a prime. We don't want 1 as a prime. Sometimes people have 1 as a prime in their definition. We don't want 1 as a prime because otherwise we could introduce 1 to the power of anything we liked at the front of this product, and we'd lose the uniqueness, which is an important thing that we want to keep. If we want a formal proof of the fundamental theorem of arithmetic, then we need to use mathematical induction. That's another thing that's covered in chapter 3. We'll come back to this result in chapter 3 if you don't do it in the lectures. But informally, if you can follow what I just did for 60, 2 squared times 3 times 5, you should get the idea of why the fundamental theorem is true. And at this stage, that's all I'm really interested in you knowing. So let's look at some examples. Here's four easy examples. The first two, in fact, we've already looked at, if you look back. But I'll let you pause the video if you want and work out what the prime factorizations of each of these four numbers are. Well, we've already seen the first two of these, as I said. 4 is just 2 squared and 6 is 2 times 3. 24 is hardly any harder. It's 8 times 3 and 8 is 2 cubed, so it's 2 cubed times 3. So we're left with 720. There are several ways you could do this. Possibly the most straightforward is to think of 720 as 72 times 10, and 72 is 8 nines. Then you collect all the terms together, and you would get 2 to the 4 times 3 squared times 5 as the prime factorization of 720. Well, now let's look at something a bit more interesting. Here's a number we met in the previous video. It's a number borrowed from my Opal card, showing $23.10. Think of that as the number 2310, and let's try and find its prime factorization. I invite you again, if you want, to pause the video and try and find the prime factorization yourself. So here we go, 2310. Once again, the factors of 2 and 5 are there immediately, so we can write 2310 as 2 by 5 by 231. What about 231 then? 2 and 5 are primes, so we don't need to do any more with them. 231, in fact, is divisible by 3, because you sum the digits, 2 plus 3 plus 1, and that's 6. And our divisibility test says the number is therefore divisible by 3. In fact, 231 is divisible by 11. 11 divides 231 because the alternating sum of the digits, 2 minus 3 plus 1, is 0, and 11 divides 0. So 231 is divisible by both 3 and 11, and if you in fact factor out the 3 and factor out the 11, you find that 231 is 3 by 11 by 7. So overall, our number 2310 is 2 by 3 by 5 by 7 by 11. It's a product of the 5 smallest primes. It's the smallest integer divisible by 5 distinct prime numbers. Now, 2310 is not a particularly difficult number to factorize, neither is anything else we've done. Factorizing small numbers, not a problem. Factorizing big numbers, and I'm talking hundreds of digits here, that's a very difficult problem. It's in fact the basis of most modern crypto systems. If somebody could invent a fast way of factorizing large integers, then we just have to reinvent how we do most of our internet commerce, how we keep our internet commerce secure. This is part of the buzz around the idea of a quantum computer, because quantum computers, if you build one big enough, can actually factorize very large integers very, very quickly. I'll leave you to investigate this idea yourself if you're interested. Now, for the rest of this video, I'm going to talk a bit more about primes, how to find them, and then I'll go through a few unsolved or open conjectures about them. But that's really extension material. You can skip the rest of the video if you want. The main part of the course will move on to looking at something that, well, at first sight seems to be twice as hard as factorizing, finding factors of one number, but in fact it's actually much easier to find common factors of two integers, and that's what we're going to be looking at in the next video. For this video, I'm going to continue on with, as I said, is really extension material, how to find small primes, and some other facts about primes that might be of interest. One simple way of finding small primes, a list of small primes, is a thing known as the sieve of Eratosthenes. And it's really very simple. You write down all the numbers up to whatever largest prime you want to go. In this case, I'm going to find all the primes less than 50. So I write out all the numbers from 2 to 50, not including 1, of course, because 1's never a prime number as far as we're concerned. And then you start from 2, the first number, and then you count off every second one and you cross every second integer out. So we're crossing out 4, count 2, cross out 6, count 2, cross out 8, and so on. As you see here, I've crossed out basically all the even integers. And 2 is our first prime. The next number not crossed out is 3, and you do the same thing. But this time you count every third integer. You start from 3 and you count 3 integers on, and that's 6, that's already crossed out. Count another 3 on, and that's 9, so you cross that out. And you continue this way. And if there's a new number that's not crossed out, you cross it out. And this will get rid of all the factors of all the multiples of 3. Then you repeat for 5. You start from 5 and you count on 5, cross out, and so on. Now it turns out here that the first number that we isn't already crossed out is 25. So we cross out 25 and 35, 45, in fact a multiple of 3, so that's already been crossed out. So that removes 2 more numbers, 2 more multiples of 5. The next number is 7. Well, you start from 7 and you count on 7 and you cross out. 14's already crossed out, 21's already crossed out, 28's already crossed out, 35, 42, or 49. That's the only integer that we're going to cross out as a multiple of 7 that's not already been crossed out. And that's where we finish, because 7 squared is 49, so we don't need to look at multiples of 11. Every multiple of 11 will already have been crossed out, every multiple of 11 less than 50 anyway. So we're finished. Every number that's not crossed out is a prime. It's a prime strictly less than 50. Now, the important point to notice about the sieve is that it's a sieve because we don't need to multiply, we just need to count. 2, then count on 2, count 2, count 2, count 3, and so on. It's just a counting exercise, not a multiplication exercise. That's why it's given the name sieve. We sift out all the multiples by just counting. Now the sieve is all very fine and good if we're just looking for small primes and we're looking for a set. If I just throw you a number with lots of digits, how do you test whether it's prime or not? Well, in fact, there are several very quick and clever tests to prove an integer is prime. They're all much faster than just the primitive trial and error we looked at earlier on in this video, or just using the sieve. It's much harder to actually find a factorization of a composite number. And by much harder, I'm talking of the difference between fractions of a second and years and years. Here's a simple example. 2 to the power of 1237 minus 1. That's got 373 digits. I put this into Maple on my Office PC, and 0.08 seconds of CPU time later, it spat back its composite. I then asked it, all right, find me the factors. Well, it took 100 minutes. In fact, more than that, I just gave up. I went away and gave a tutorial, I think, and when I came back, it's still not finished, and I thought, well, that's enough. So this is the difference between fractions of a second and hours. Well, in fact, if I'd left it running, it probably would have taken weeks, months, or maybe even years to actually find factors of this number. That's the difference. That's why, that's an illustration, I should say, of factorization being much more difficult to prove or to find than the proof that something is composite or not. The useful Maple commands, the Maple commands I used here, by the way, are isPrime, it is prime number, it comes back true or false, and ifactor, which finds integer factors. You'll find, by the way, that other computer algebra systems will have similar commands in them. And this is the point I made earlier. Current cryptographic methods really rely on the fact that it's very hard to factorize large numbers, but quantum computers can do so very quickly if you can build one big enough. And that's why they pose a threat that they do to current cryptographic methods. If you're interested in learning a little bit more about this, then we cover these in our two courses, Math2 400, Finite Maths, and Math3 411, Information Codes and Ciphers. Let's turn on now to look at some open results and simple other facts about primes that we can talk about. A prime of the form 2 to the power of n plus 1, so a power of 2 plus 1, that's known as a Fermat prime, after the French mathematician Pierre de Fermat. Fermat primes have some interesting connection to problems in geometry, and our courses Math3 521, Algebraic Techniques in Number Theory, and Math3 711, Higher Algebra. In those courses, we look at the connection to Fermat primes in these problems in geometry. It's not too hard to show that if 2 to the n plus 1 is prime, then n in fact must also be a power of 2. So n is 2 to the k for some k. It's a proof you can have a look at in chapter 3 of the course. It's not very difficult. We only know 5 Fermat primes, 3, 5, 7, 257 and 65,537. I'll leave you to work out what the k is, or 2 to the k plus 1, for these things to be to give these Fermat primes. What we don't know is whether there are any others. A prime of the form 2 to the n minus 1 instead is known as a Mersenne prime, after another French mathematician. It's not too hard to show that if 2 to the n minus 1 is prime, then n in fact must also be prime, and that's another result you can look at in chapter 3 of the course, in the problem set if I remember properly. Now you should also be aware that not every number of the form 2 to the p minus 1 for p prime is prime, and here's a counterexample. 23 is prime, but 2 to the 23 minus 1, well, here's its factorization. It's not a prime number, it's a composite. We do not know if there are infinitely many Mersenne primes or not. 2 primes that differ by exactly 2 are known as twin primes. 3 and 5 are twin primes, 29 and 31 are twin primes. There are many primes that are not parts of twins. We don't know if there are infinitely many of these. We don't know if every even number larger than 2 is a sum of 2 primes. It's very easy to pick an even number larger than 2 and write it as a sum of 2 prime numbers if the even number is quite small. But when the numbers get large, well, that can be quite hard because we don't know all primes necessarily. The Goldbach conjecture is that in fact it is true that every even integer larger than 2 is a sum of 2 primes. And the Goldbach conjecture has been checked for numbers up to about 17 digits. But we don't know whether it's true for every even number or not. There are many other facts about primes that are known and many other conjectures as well, but we're going to put them aside and go on with the rest of the course to looking at what, as I suggested earlier, sounds at first sight to be a harder problem, looking at not factors of one number, but factors of pairs of numbers. And that's going to be in our next video.